Right. Hello again, and welcome to your last advanced geometry lecture. Hope you guys have had a good time. Hope you've learned something. Today I will basically just be doing a few things which I have considered useful, that I found useful while doing Olympiad geometry. I don't think they're particularly difficult, so you should get this easy peasy. But you should definitely know what they are. The first one you might have heard before, but there might be a few of you which haven't heard it, and it is super useful. So, and I will also elaborate on it a little bit to maybe show you some stuff that you haven't seen before. The next one will be, again, something that's useful. Doesn't come up too often, but when it does, it's very useful. And then I've got a few other things, and we're not sure if I'll get to all of them, but hopefully I will. And so the first one is called the South Pole Point Theorem. Basically, you have a triangle with actually intelligently named points. I should have done this better, but let's just give this a proper diagram. A, B, and C. Then the South Pole Point Theorem states that if you take the angle bisector of A and the perpendicular bisector of BC, these 2 points intersect on the circumcircle of the triangle. And by convention we generally call it S, but whatever, you can call it whatever you want. Now, I fully expect most of you to have seen this before. However, there are a couple of interesting points which can be said about this. And also, there's a warning that comes with this one, and that is, in like an official Olympiad, like the PAMO or the IMO, you cannot actually use the term South Pole Point Theorem. It's a South African name for this theorem. You can just claim it as well known, or introduce it as a lemma. The proof is pretty trivial. Essentially, you have arcs BS and SC are the same length because S is the midpoint of BC. So the angle subtended by SC and SB are the same, which means S is an angle bisector. Assuming A1S is the perpendicular bisector of BC, of course. But I don't know how much you've actually explored this particular configuration, and there are quite a few interesting properties that come up when it comes to this particular configuration. Namely, that this point here, which is often referred to the anti-South Pole point, or the North Pole point, subtends, I mean, this is fairly obvious, but a lot of people forget it, subtends an angle of 90 degrees, and obviously ds is a diameter. But this actual construction, although fairly trivial, does actually pop up quite a number of times. You'd be surprised how often it comes up. And it's an interesting example of a fixed point. So given any point where A is variable, points D and S are fixed. However, there is still more that can be done. Firstly, an interesting one is that if you consider the circle centered at S with radius BC, it passes through, I believe, I hope I'm not wrong about this, the incenter of the triangle. So if I draw the other angle bisectors, you will find that they intersect on the circle. This is not particularly hard to prove, and in fact we will prove it now. So obviously, if you have a circle centered at S with radius SB, it's going to go through C as well, because SB is equal to SC. And the rest is just an angle chase. So if we call this point I, we just do the angle chase, of course. So where shall we start? So we want to find what SIC is equal to. So notice that SIC is equal to IAC plus ICA. And notice that IAC is half of angle at A and ICA is half of angle at C, which means that SIC is equal to half of the angle of A plus the angle of C, which is half of 180 degrees minus the angle at B, which is 90 degrees minus half of this angle, which is IBC. And yeah, so that gives us what this angle is equal to, 90 minus IBC, for instance. And then notice that ICS is equal to ICS is equal to ICB plus BCS. Now BCS is equal to BAS, which is equal to half of angle at A, and ICB is equal to half of angle at C, which means that ICS is equal to half of angle at A plus half of angle at B, angle at C. And notice that the half of angle at A plus half of angle at C plus the half of angle at B is equal to 90 degrees, because A plus B plus C is equal to 180 degrees, which means that half of angle at A plus half of angle at C is equal to 90 degrees minus half of angle at B, which means that SIC is equal to SIC is equal to SCI, which means that IS is equal to SC. And there we go. I lies on that circle. That is a pretty important result, and it can come in useful. I think the other interesting case is that I'm not sure about this, but I have a feeling that the external angle bisector lies over here. So the center of the X circle opposite A should lie at this point here. And the easiest way to check that is by just considering the angle bisector at the external angle bisector at angle B. Yeah, there we go. And we have the X circle center opposite A lies on this south pole circle as well. And we can quite easily see that just by drawing the circle. As you can see, tangent to all three sides. Now, I think that's pretty much all I can say about the south pole configuration. There might be a few other things, but oh, actually, no, that's not true. There is one more thing of importance. Now, I think it might use this circle as well, so we will leave the circle, but we'll get rid of the angle bisectors. And that, I think the theorem, well, not theorem, but lemma, I believe you can claim this, but I'm not certain, so don't quote me, is that AB times AC is equal to SA squared. I believe this is the theorem, but let's check. The proof should just be similar triangles and such. In particular, we have a couple of similar triangles. We have this angle BAS is equal to angle, actually we should give this point a name. Let's call that T, because why not? And actually we should call this one N. Call this one N for North Pole Point. Now, we have that BAS is equal to SAC because that is an angle bisector. And we have that angle ASB is equal to angle ACT. So we have two angles equal, which means we have a pair of similar triangles, which means we have some ratios. So the ratio that we are interested in is going to be AC over SA is going to be equal to SA over AB. And then when we carry things across, we get AB times AC is equal to SA squared. Okay, that's kind of messed up, but you get the idea. Maybe if I put a slash n. No, it doesn't like slash n. Okay, slash slash maybe. Yes, it does. Okay, cool. Yeah, so that's where you get the proof from. Just that pair of similar triangles. Now this actually has popped up a bit. In particular, because I think if you look at this, you get that a bunch of lines form a harmonic or something. But yeah, this can pop up occasionally and is pretty useful. So let's move on now to the next useful thing. Right, the next useful thing that I have used on occasion, not as common as the previous one, but still definitely, is that if you have a circle and you have a triangle, and then you have a point, and let's call this point, oh god, I've messed this up again, haven't I? Not a big deal, just rename things. Let's call this point X, and let's call this point A, let's call this point B, and let's call this point C. Then, if you take perpendicular lines from X, let's just make sure we've got all the sides here. So extend these lines out all the way. Draw perpendicular lines from X to AB, perpendicular line from X to BC, and a perpendicular line from X to AC. And then you look at the points. Whoops. Points D, E, F. Then D, E, F is a straight line if and only if X is on the circle. If X is not on the circle, then it's not a straight line. If X is on the circle, then it is a straight line. So this can be used to prove two things. It can be proved to use collinearity of a bunch of points if you can find a specific point X. Alternatively, it can be used to prove cyclic quads if you've got like a triangle ABC and you want to show that X lies on the same circle as it, then you can use this nice property. This property is called the Simpson's line. I can't remember if I mentioned it. And you can claim this, absolutely, that it is a well-known result. And I think we should go ahead and prove it. The proof is pretty basic. It's just a bit of an angle chase and then using vertically opposite angles. But the angle chase, I believe, is not the most trivial thing in the world, so let us do that. So first let us draw a X, and we're going to chase this angle here. So we look at the angle DEA. Now we have that ADXE is a cyclic quad, but because opposite angles are 90 degrees, so they sum to 180, so it's a cyclic quad. And therefore we have angles subtended by a chord that we also have that's equal to DEA is equal to DXA. And similarly we have that XEFC is a cyclic quad. And so we have, if I can select the right one, that FEC is equal to FXC. Now we just want to show that AXC is equal to DXF, and obviously if that is the case, then we will have that DXA is equal to FXC. Just by, you can take the difference between them, and you must have that those two angles are the same. So let's look at angle XDF. This one I think we will give a different color to, so XDF, and let's call this one red. Okay, XDF is going to be equal to XAE because of angles subtended by a chord. Furthermore, we have angle X wait, hang on. That won't quite work because we don't know this is a straight line yet. Okay, actually no, I am being a moron. Yeah, let's get rid of this. So we know that DXFB is a cyclic quad because angles 290 degrees, which means DXF is equal to 180 degrees minus DBF, opposite angles, subtended, and therefore, and also in the cyclic quad AXCB, we have that AXC is equal to 180 degrees minus ABC, which means that AXC is equal to DXF, which means that DXA is equal to FXC as required, and thus proving that DEF is in fact a straight line. Yeah, just another little useful piece of information. Now, moving on to the next one. Oh, actually, I should... the exact statement, I guess, if you want to write it down, is that given a triangle ABC with circumcircle gamma, then, and a point X in the plane, with perpendiculars XD, XE, XF dropped to the sides AB, BC, and CA respectively, the line DEF, so D, E, and F are collinear if and only if X lies on the circumcircle of ABC. Right. The next one that I want to talk about is called the external angle bisector theorem. This is a very short one. The reason why I point this out is because you've definitely heard of the internal angle bisector theorem. If you haven't heard of the internal angle bisector theorem, then you should probably go talk to the person who's running intermediates and tell them why they didn't teach you this. But it's pretty straightforward. So firstly, if you are unaware of what an external angle bisector is, despite the fact that I've already mentioned what it is the angle bisector of this particular angle here. So the internal angle bisector is, of course, the internal angle bisector of, the angle bisector of BAC. The external angle bisector is this sort of DAC, the reflex angle of BAC. Sorry, not reflex. The supplementary angle of BAC. Now, the interesting fact about external angle bisectors is that the external angle bisector is perpendicular to the internal angle bisector. This is fairly evident, but if you're unsure why, it's just that if this is A and this is 180 minus A, then this is 90 minus A over 2, and this is A over 2. And so if you sum those two, they must be complementary. Right, now, the reason why I say that this particular theorem is actually quite simple is because it is literally the exact same statement as the internal angle bisector theorem. So that means if we have the external angle bisector of A, then we have the following theorem, if I can find the text, there it is. We have that BE over E over EC is equal to AB over AC, or I guess more correctly, whoops, what the hell. I guess more correctly we should probably say something like EB over AC. Now this is also true for the internal angle bisector if you just have E over there, but it's also true for the external angle bisector, and I don't know, it was weird. I only learned this theorem when I was in like grade 10 or grade 11, or like way after I'd been doing Olympiad maths for like, no one told me this for a long time. So yeah, if you're seeing this now, if this is the first time you're seeing it, you're welcome. If it isn't, then nothing to worry about. But yeah, it's pretty simple. And that brings us on to the next thing. This is such a simple diagram, I'll just bring it on to the previous one. So this next sort of little lemma thing, this one you cannot claim in a... actually, can you? No, I think you have to prove this one, I'm not sure. It's pretty well known, so the proof is fairly straightforward, or at least you should know the proof off by heart at some point. And that is, let's just draw the configuration. We construct the incircle by first doing angle bisectors. And we're going to need perpendicular line from, we're going to need a point first. Perpendicular line to C, and then we construct the circle. Wait, what? I'm fairly sure that's the perpendicular, but have I just drawn this so it's really isosceles? Yes, it is. Let's draw it less isosceles. Okay. Then we hide this. Okay, maybe not this one. Settings, subject. And then also we construct the external angle bisector. There it is. And we're going to need a point. And then we construct the tangency point of the X circle to this point, which I'll just draw so you can see that it is in fact correct. And why not, while we're here, let's draw in this there so you can see what I'm getting at here. And then we don't need this one, so we will, can I just, no, damn it. There we go. Okay, so let us construct this point there, and then let us go right across. Now, this little lemma states that if we rename all these points to actually intelligent names, let's call, open up the settings here, let's call this one I. Call this one. Ooh. What is going on? Chill. There we go. Okay, let's call this point D. And let's call this point F. And let's call this point E. And then let's ignore this point completely. We don't need that one. Right. So the little lemma states that F, E, and A in this particular diagram are collinear. So the actual statement, pardon me, is that if you have a triangle ABC with the incircle such that is tangent to BC at D, if E is the antipodal point to D, i.e. the point diametrically opposite from D in the incircle, and F is the point of tangency of the X circle to BC, then A, E, and F lie on a straight line. The proof of this is fairly straightforward by just simply drawing one line, just tangents. So if we draw the tangent at E to the circle, we notice that this tangent is perpendicular to ED, which is perpendicular to BC, which means that this tangent is perpendicular to BC, which means that the incircle is of this triangle here of ABC is the X circle opposite A of this smaller triangle, which is yet to have names but doesn't really need names right now. And therefore there is a similarity between this diagram here and then the bigger diagram, which means that by just doing similar triangles, or if you're more advanced, homotopy, by just considering the ratio of, say, AE over AF, you will get that, well, not quite AE over AF because that's cheating, but say H in this case, AH over AB, by then constructing such a triangle, such a point F, by taking AE and then along there extending it the same length, you will get that this point F is precisely this external tangency point, which means that they must be a straight line. That particular approach is called homotopy. If you want to learn more about it, there is a video that I did last year on homotopy. You can go check that out. I can't remember if it's any good. I hope it is. But yeah, it's an advanced, homotopy is an advanced technique. It's pretty cool, but I'm not going to talk about it much. Although this lemma does come up quite a lot in homotopy style proofs. So yeah. If you want to see an actual use for this particular lemma, you can check out 2008 problem 6, IMO of course. It's one of my favorite problems that's ever been in the IMO, so take a look at it if you like. Right, so that was number 4, and right, so we have time for one more, I reckon. This is going to be a reasonably long one because there's a lot that one can say about this, but I don't know how much you have seen it before. Right, so I'm being stupid, I want to duplicate. Cool. So this next one is called the Euler line. Some of you might have heard of the Euler line before. It's a really cool piece of geometry, but if you are unaware, this is what it states. I generally like to group in the Euler line with the 9-point circle a lot. You will see why that's relevant in a second. So basically, we're just going to construct a whole bunch of circle centers and show that they all lie on a line. So the first one is the circumcenter. So we construct the circumcenter by doing perpendicular bisectors and then drawing the circumcircle. Right, there's a circumcenter, and in fact let's call this one its proper name, which is of course O. Then the next important point on the Euler line is the centroid, which, if you're unaware of what the centroid is, it is the intersection of the medians So in this case, D and E are the midpoints of the side A, C, and B, C. I refrained from doing the midpoint of the third side because it's not necessary for the construction, but you must understand that obviously these Sevians, the medians in this case, are concurrent, so if I did draw another one, it would go through this point here, which of course is well known to be called G. And let's move this around a bit so we can get some more space in between our points here. Okay, that's probably good enough. So let's then get rid of these construction lines, and might as well get rid of these ones as well. Now, the third point on our line is going to be the orthocenter. And that I don't need to do those points, I just need to call that there. Of course, the orthocenter is well known to be called H. And it is the intersection of the altitudes from A to the opposite, the vertices to the opposite sides. But you knew that already. The next point that lies on the Euler line of importance is the 9-point circle center. Now, if you recall previously what the definition of the 9-point circle is, we construct the perpendiculars to the sides, and we could construct the midpoints as well, but in this case we only need 3 points, so let's just construct the midpoint and then the feet of some perpendiculars, and then draw the lines. Whoops. And then afterwards, once we have drawn all the points, I will prove why they all lie on a line, one at a time. And the 9-point circle center we will call, I guess, N. Why not? Settings, okay. Right, so as we can see here, 4 points all lying on a line. Cool, and we've got some points, residual points left over. Let's get rid of those for now. Might need them later, but not right now. There are a whole bunch of other points that lie on the Euler line, but they're generally very non-trivial and you will not really necessarily always need to use them. But the 9-point circle center, the orthocenter, circumcenter, and the centroid are all very, very important points that you need to know are all collinear. And now let's go about proving such a theorem. So let's first show that the orthocenter, centroid, and the circumcenter all lie on a line. And the way we're going to do this is by constructing the perpendicular from O to this point. Now recall that this is a perpendicular bisector, which means that if we draw this, that is the midpoint. Oh god, come on. That is the midpoint of the side, which means it'll go through the centroid, and then let's draw the perpendicular line from A to C, and that's going to go through H. Now, we want to show that the HGO is a straight line. The way we can do this is by just showing that there are similar triangles, or say for instance that these angles are equal. And that, I can't remember if that's particularly difficult. But yeah, I think the way that this is done is by looking at ratios. So let us consider a bunch of ratios, and let's take a look at what they are. In particular, let us look at OK over AH. Now, we know that AG over GN is in the ratio 1 to 2, so it would be convenient if OK to AH was in the ratio 1 to 2. So let us draw the midpoint of AH. And we want to show that LH and OK are the same length. Now, I think actually it might be easier to just go via the 9-point circle. I'm just trying to think. Should I just do it via the 9-point circle? Okay. Yeah, let's just do it via the 9-point circle, because I think it'll actually just be the easiest to do the 9-point circle center first, and then to do the follow-up ones. So let us call this foot something. M is no, actually that's broken. Obviously, this middle point here should be M. M. And then this point should obviously be called D. And let us draw obviously ND and NM. So the assumption we're going to start off with is that HNO is not necessarily a straight line, but N is the center of the 9-point circle. We proved this in Monday's lecture, I want to say. And so we know that ND is equal to NM is equal to N. Yeah, we're going to call that one L. For now, we can keep that L. And furthermore, we know that MNL is a straight line that subtends 90 degrees. Well, okay, so the line ML subtends an angle of 90 degrees, which means it passes through the center, which means it passes through N, which means LNM is a straight line. Furthermore, we now want to show that OM is equal to HL. I think that is the way we want to do this. And the way we are going to do that is by oh yes, sorry, I'm being stupid. Not LH. We're going to show that it's equal to AL. We're going to show that OM is equal to AL. We're going to basically show that this thing's a parallelogram. Right, and the way we're going to do that is to use various factors. I've done this before several times, but we will persevere. So AO is, of course, the radius of the circumcircle, which means it's equal to R. In fact, actually, let's write that down. AO is equal to R. It should be capital R. Ooh, let's do weird things. AO equals R. Now, we know that the LM is the diameter of the 9-point circle, which means it is the length of LM is half the diameter of the of the circumcircle, which is just the radius of the circumcircle, which is r, which means Lm is equal to r. So type in Lm is equal to r, and oh my gosh, Lm equals r. So to show that ALMO is a parallelogram, we only need to show that AO is parallel to LM. And to do that, we will just basically chase some angles around. In particular, we will chase, we know what this angle is equal to. Well, I mean, we can work out what this angle is equal to, so we're going to look at OAH. Where is text? There we go. Okay, so now OAH is going to be equal to CAB minus OAC minus HAB. But we know from our well-known useful lemma, in fact, actually, I probably should have included that here before, but I'll just mention it now. I did mention it previously, but I'll mention it again, and that is that H and O are isogonal conjugates. This is a well-known thing. You can claim it. It's a very useful piece of knowledge. You should definitely write it down if you haven't. So we know that HAB is equal to OAC, and we also know that OAC is equal to 90 minus angle B, which means that HAO, which is equal to LAO, is equal to angle A minus 180 minus 2B, i.e. 90 minus B times 2, which means that LAO is equal to A plus 2B minus 180. And notice that A plus B plus C is equal to 180, which means if we add C and subtract C, we get that it's A plus B plus C plus B plus minus 180 plus B, or plus C. Hang on, let me just write this down. So we have that A plus B, so 2B minus 180 is equal to A plus B plus C plus B minus 180 minus C, which is equal to B minus C. So we have that LAO is equal to B minus C. So let's look now at HLN. Now, this might be slightly more complicated to work out because of the construction of this particular these particular points, but it shouldn't be too bad. So B minus C should be given somewhere else. Should come from somewhere else. We want it to be this one, which means it should be also equal to this one. Yes, of course, here we go. Here is the I think it's should be this, because then we get that in half. Yes, okay, so no, that's fine. I feel like I'm missing an obvious midpoint theorem thing around here somewhere. But I'm not sure where it is. So that's not a huge deal. But yeah, so we know that HD is equal to dk by the properties of the 9-point circle. And I want that OK, oh yeah, so OK is equal to OA, which means that OAK is equal to OKH, OKA by base angles of an isosceles triangle, which means that OKA is equal to B minus C as well. And now we want that HDN is going to be B minus C, but that's only true if that's a straight line, and we have not proven that yet. I feel like I'm being really stupid about this. I am being really stupid about this. I'm absolutely being really stupid about this. So if we think about this from a more logical perspective, in which I have, like, consider it a different universe where I haven't been like misleading you for the past 15 minutes or whatever it is. The way that you prove this rather obviously is by, yes, we do 9-point circle, but the way we do it is by just looking at the most obvious way to check if something, to find the center of a circle, and that is by drawing perpendicular bisectors. If you draw the perpendicular bisector of MK, then we know that the point, these 9-point circle center must lie on this line, and also because of midpoint theorem, it must lie specifically a ratio of 2 ways. So, and if you do the same thing with PQ, because you've got all these parallel lines running around, basically, you know that basically these perpendicular bisectors must intersect on midway between H and O, which means N, sort of vacuously almost, lies on the line HO. And then once you've got that, you get basically all those other properties that I've been moaning on about for the past, I don't know how long. Oh God, don't want that. And so you have HNO as a straight line. And since you have HNO as a straight line, we know that we can do other things. In particular, I believe if we draw HN, if we draw HN over, we get that OK is equal to KR, because LNK is a straight line. Actually, that should probably be good enough, I think. Okay, yeah, but anyway, so OK is equal to LR, because AL equals LH and ON equals NO. So by just similar triangles, this is, we have, in fact, congruent triangles. This whole configuration ALHN is congruent to the configuration RKON, which means OK equals KR equals AL equals AH. And therefore, we have OK, and OK is equal to half of AH, and therefore, if we draw the line OK, which is the median, we know that the point that is precisely 2/3 down AK must lie on the line HO, but we know that point is G, so G lies on the Euler line. And that is me done for the week. Good luck with your final test tomorrow, because you'll be getting this on Thursday. I hope you've had a good time despite the ridiculous circumstances, but you know, everyone's staying safe, so that's good. And yeah, good luck with all kinds of geometry and your Olympiad career, etc. I hope I haven't scared you off too much. This week has been absolutely crazy for me, but I won't take up any more of your time. Cheers.